Yep, go ahead.
Go right ahead. Good morning, everyone. Welcome. I'm Carolyn Remick from the Berkeley Water Center here on the UC Berkeley campus. It's a pleasure to welcome you to be part of this.
Considering them together offers substantial benefits. Economic benefits, environmental benefits, some could argue political and social benefits as well. And so we need to do that, and that's really my conclusion. And I would simply add at the end, the reality of climate change, which was touched on a little bit this morning, although not very much, affects both of these issues. And I'll come back to that as well. Okay, so first, water for energy. The energy cycle requires substantial amounts of water, from mining to generation to distribution to end use of energy to waste disposal. The energy fuel cycle entails water as well. And we've spent a lot of time thinking about risks associated with the energy fuel cycle, but not so much about water. And it's time that we did that, because water is an input to every one of these pieces of the puzzle. And I would also note there are water quality implications, not just water quantity requirements, but water quality implications of each of these pieces of the fuel cycle as well. Substantial amounts of water are required for the production of energy. If we think simply about generation, the largest withdrawal of water in the United States, the largest single end use of water in the United States is for power plant cooling. It's about 45%, maybe a little more, of all of the water withdrawn in the United States goes to power plant cooling. Now, an important distinction is the distinction between withdrawal and consumption of water. The vast majority of that water is not consumed. It's withdrawn, it's used for power plant cooling, it's put back in the lake or the river a couple minutes later, a few degrees warmer, and it's available typically for downstream users. That's a little different than the biggest consumer of water in the United States, which is irrigated agriculture, and that's a consumptive use. So think about that distinction. Water people like to think about a distinction between consumption and non-consumptive uses of water. But nevertheless, the largest single withdrawal of water is for power plant cooling. In arid and semi-arid regions, in the western United States especially, the demand for water can be a substantial amount compared to the flows of water, the amount of water that's available. And so in water-constrained regions, that's the withdrawal, not just the consumptive use, but just the withdrawal alone can be an important piece of the puzzle. Far more water is required for nuclear and fossil fuel generation than for most renewable systems, depending on the cooling system type, and I'll come back to that as well. So if you care about energy policy, and if you're interested in scenarios of energy development, different scenarios of energy development give you different water requirements. And again, I'll come back to that. So here are a few examples. The y-axis is the consumptive use of water, not the total withdrawals, but the consumptive use of water, because energy systems consume water as well, in cubic meters per 1,000 kilowatt hours of electricity produced for a variety of different energy options. Fossil fuel with once-through cooling systems, fossil fuels with cooling towers, nuclear, geothermal at the geysers is very water intensive because it's fairly low temperature system. Photovoltaics, a little bit of water, and some people think the actual number is 0, but if you generously attribute a little bit of water for washing panels every now and then. Solar thermal electric has a water requirement, wind is basically 0. So the water intensity of different energy systems varies, depending on your assumptions, and there are ranges associated with each of these. But there are also constraints, and growing constraints. And here are a few headlines from 2007, 2008, when there was a serious drought in the southeast of the United States. Drought could force nuclear plant shutdowns, shrinking water, rising tensions from Energy Biz insiders. And you can read them as well. Maryland County denies cooling water to proposed power plant. A growing controversy, a growing conflict between energy policy development and people who are increasingly concerned about water availability. The interaction between water and energy is increasingly playing a role in not just practical plant operations, but in development plans. And here's another example. Again, very severe drought in the southeastern part of the United States in 2000, I think this was 2007, and an article about nuclear power plants where cooling systems were going to be affected either by limits on water availability or by constraints on the temperature of the water that cooling systems could put back in rivers for ecosystem reasons. If the temperatures of rivers go too high, fisheries are affected, ecosystems are affected, and more rivers have temperature limits. And when low flows happen during droughts and temperatures go up, then all of a sudden cooling systems can exceed those cooling limits on certain rivers. And so there were deratings or shutdowns of nuclear power plants. And I would note fossil, so big coal plants as well. But certain kinds of renewables can be water intensive as well. There are growing numbers of central solar thermal plants that are being built in the California desert. Increasingly, the California Energy Commission is requiring specific kinds of cooling systems, low water use cooling systems, dry cooling in particular, before they will permit a central thermal plant in the desert, because the water is not available in some of these dry regions. Now, dry cooling is more expensive. Dry cooling has an energy penalty associated with it. It reduces the efficiency of some of these plants, or the outputs of some of these plants. So there's an economic cost to some of these water constraints, but we need to be aware of them. The Pacific Institute, my institute, did a study a year ago on the water requirements of different energy scenarios in the Intermountain West. The citations down here at the bottom, future water needs for electricity in the Intermountain West. And we looked at the current water requirements in million gallons per day of the existing 2010 energy mix. We looked at the current trend scenario up to 2030, and that suggested that, in fact, there would only be a very modest increase in the water demands, in the total water demands, by 2030. But then we also looked at current trends, in other words, the expected mix of future additions to energy in the Intermountain West, fossil fuel, nuclear, renewables, under current trend scenario from the Energy Information Agency, but with a 25% dry cooling requirement, which is a different kind of cooling requirement than is currently in place, or a 50% dry cooling requirement, or an expanded renewable scenario, with more of this low water using cooling systems. And as you can see, different scenarios have different water requirements. I mean, the bottom line is the choices we make about energy systems and cooling systems have an incredibly important impact on the total water demand in this region, in the Intermountain West, which is typically a dry region, and very substantial ones, cutting water demands by more than half in some of these scenarios. The choices we make have a big water implication. All right, so the other side of this, of the water for energy system, is the energy for water systems. It turns out that our water systems also require a tremendous amount of energy to collect and convey water, to treat water to the quality we want it, to distribute it from where we get it to where we use it. There's a tremendous energy demand in the end use of water, primarily for making hot water at home. Wastewater treatment has an energy demand, and that also is a factor that we've not thought much about. And like the other graph, this is a graph that shows some of the energy intensities of different water choices. So seawater, and the units are kilowatt hours per acre foot of water. And an acre foot of water is about 320,000 gallons of water, for those of you who care. So seawater desalination is extraordinarily energy intensive. It's sort of the big one. It's one of the reasons why desalination has not been a particularly successful technology at this point, because it's very, very expensive. There's a big capital cost, but there's also a big energy cost, and energy's not cheap. Groundwater pumping, and I would note this is the energy intensities of water systems for Southern California, this study we did. Reclaimed wastewater, groundwater is fairly low. Brackish water desalination is much less energy intensive than saltwater desalination for technical reasons. Delivery of water to Southern California through the Colorado River Aqueduct across the state, or from the State Water Project from Northern California and the Sierra to Southern California has an energy cost as well. The choices we make about water policy have energy implications, and increasingly that's a factor to be discussed. So the State Water Project turns out to be the single largest user of energy in California. Primarily the pumps that pump water over the Tehachapi Mountains into the Los Angeles Basin. Some of the biggest energy pumps, some of the biggest water pumps and energy consumers in the world. It requires an average of about 5 billion kilowatt hours per year to operate the State Water Project. And that previous graph that showed the State Water Project demand is primarily for pumping water over the Tehachapi into the Los Angeles Basin. This is just a specific example. You can actually look for any region at the energy costs of the different choices in that region. This is for San Diego. It turns out the largest user of energy for our water systems is end use. It's heating water in your home. But the second largest is source and conveyance. This is kilowatt hours per acre foot of water delivered. Is conveyance to get water to San Diego, because much of their water is imported. Wastewater treatment, distribution is fairly low, water treatment at the end. Just to give you an example, and you can do this for any region you want. So there are key energy water connections, and it's beginning to affect policy. So the Mayor of London is an example, rejected plans for a desalination plant on the grounds of the energy intensity. Western Australia, in Perth, they just built some desalination plants, and in order to compensate for the greenhouse gas emissions that would be associated with that, they required that there be about 80 megawatts of wind turbines built in the region to partly offset the carbon footprint of that desalination plant. Thames Water, one of the water utilities in England, estimates that their energy bill is already about 17% of their total operating costs for providing water, and it's rising fairly rapidly. And I've talked about the power plant concerns for derating or shutting down during droughts because of temperature limits. Another example, we tend to think about energy efficiency as a key thing. It turns out that some of the most efficient ways of saving energy are saving hot water. So you run a 60-watt light bulb, an incandescent 60-watt light bulb, for 14 hours. That's the same energy footprint, if you will, as a 5-minute shower or running your hot water for 5 minutes. There's a lot of energy embedded in hot water. So efficient shower heads turn out to be an incredibly good way to save energy from a cost-effective point of view. California, as we know, is beginning to regulate greenhouse gas emissions. That's including water utilities. Water utilities are going to have to think about their greenhouse gas footprints, their energy use associated with their water requirements. And I've made this comment already. Some of the cheapest energy efficiency savings can come about through water efficiency programs instead, and that result comes from a California Energy Commission report. There's a climate link. All of these water energy links are connected to climate through the emissions of greenhouse gases. We all know, I believe, that some climate change, perhaps quite significant climate change, is already unavoidable. In that context, we have to move to avoid the consequences we're going to have trouble managing, but we're also going to have to learn how to manage those impacts that can't be avoided. Many of those impacts are water-related. The hydrologic cycle, evaporation, formation of clouds, condensation, precipitation, runoff, that is the climate cycle. And as the climate changes, we're going to see changes in water availability. And for example, in the western United States, some of those changes are likely to be for the worse, not for the better. The model suggests, for example, that the Southwest is not only going to get hotter, it's going to get drier, which is sort of the opposite of what we would want if we had a choice about what these impacts are going to be. Let me close with some recommendations and a little bit of a summary. Water and energy are tightly linked. Those links are poorly understood and rarely used in policy. Decision makers, corporations, the public should better integrate energy issues into water policy and water issues into energy policy. The Public Utilities Commission, and Cindy can talk about this much more than I, deals to some degree with energy and some degree with water, but has a little bit of trouble, I would argue, in integrating the two of those things. Our energy utilities don't do much on the water side. Our water utilities don't do much on the energy side, and they would all benefit from doing more in an integrated fashion. The failure to link these issues, I think, is inevitably going to lead to disruptions in the supply of both water and power. Power when we're constrained because of temperature limits or because of water availability. Water when there are constraints on energy or the kinds of energy that are available. Water efficiency efforts can save substantial amounts of water and energy at a lower cost and faster than new supply. The Pacific Institute, where I work, does a lot of work on water use efficiency in agriculture and the urban sectors as well. And one of the things we've spent some time looking at is the cost effectiveness of water efficiency savings. Dan showed some of those cost curves of conserved energy that he called them McKinsey curves, but McKinsey didn't invent them, although they've done a great job of promoting them. It turns out that a tremendous amount of the economic benefit of water efficiency comes about if you're also saving energy. So if you only look at clothes washers and the amount of water that's saved by efficient clothes washers, it's sort of marginally cost effective. But if you include the water savings and the energy savings and the detergent savings, because it turns out they use less detergent, they're tremendously cost effective. And that's an example of integrating these issues sometimes lead to different policy outcomes than you would otherwise expect. And the climate implications of both water and energy policy are significant. There are large opportunities for fast, cost-effective reductions in emissions by dealing with these two resource issues together. I'm going to stop there. I would just note, it was mentioned I had a book about bottled water that came out, but we actually have, the Institute has a new book that's just come out about a month ago called The 21st Century U.S. Water Policy from Oxford University Press. We talk about federal water policy and what the appropriate role ought to be in the 21st century. There's a chapter in there on energy and water that's relevant for some of this, and it might be relevant to some of you. Thank you very much.
Thank you so much. Our next speaker this morning is Dr. Cynthia Truelove. Dr. Truelove leads the Water Energy Initiative, which is part of the Water in the West program at Stanford University's Woods Institute for the Environment. Prior to joining Stanford, she was the Senior Water Policy Analyst in the Division of Policy and Planning at the California Public Utilities Commission. She was responsible for building CPUC's water policy program across the arenas of water conservation, water use efficiency, the water energy nexus, and the water and climate change programs. She disputes this, but I think she's often credited with as being the originator of the term the water energy nexus as it's commonly used in California. She also serves on the state's climate action team as an advisor on water and energy. Please help me welcome Dr. Cynthia Truelove.
As a sociologist and a little bit of a comparative historian or, social ethnographer or whatever is left over in me, I have to give you a quick history on that term. In fact, I came to the state in 2008, and it was in around 2005 that California Energy Commission, Lorraine White, who was a staff member there, combined with a number of consultants, Lori Park, Bob Wilkinson, and some others, who really came up with the notion of water energy nexus in its California usage and implication. So I'm hardly the originator of the term, but a convinced soul I am, and so I've spent the last 4 years trying to push rocks up tall mountains, and whatever other metaphor you'd like to use, along with others, to try to operationalize what Peter has said so eloquently. So what's the deal? He's very convincing, he's right on. the opportunities for saving, and I particularly work in the energy for water side of things. What's the deal? Why is it so hard to really come up with a state energy policy that is integrating water and energy, either energy efficiency or demand management, that in the water sector that reduces energy or captures renewable energy from the water sector? When one hears about the benefits, it doesn't seem so hard to do. And I've been threatening to write a paper that's something like water and energy, it's all in the weeds. Because when it really comes down to it, you heard both Steve Weissman and Dan talk this morning about cost effectiveness, and Peter talked about cost effectiveness. You know, I guess as a political economist, I would also say what cost effectiveness really is a pact. And it's a pact, it's a business model and a pact between the utility sector, be they public or private utilities, and the state. And energy efficiency in California, which was largely born after deregulation in 2000 forward, was a pact. The energy efficiency program that we have, and it has changed, it has evolved over time, is a pact between the utilities and the state. The way that pact is interpreted is, in a simplistic but very complicated way, through our cost effectiveness evaluations, which are very elaborate formulas that the Energy Division, for example, of the California Public Utilities Commission uses to determine what makes sense to fund from the ratepayer perspective. How to get the most out of your dollars if you're a ratepayer in California, such that we save energy without increasing your rates. Basically, that's very simply what it's meant to do. When you try to combine something like water and energy, our cost effectiveness approaches are not designed to give any value to water savings. Now, we know that in California we want to save water. We know we actually have a state mandate to save 20% by 2020. We know that empirically we can assess either the direct energy savings of, let's say, in-use savings of energy in water, like hot water appliances. We know that you can actually look at what's the embedded energy, and I'm going to come back to this in a minute, the embedded energy in water. All of the energy invested in water to the point it gets to, and you can do it up to any point, but let's say up to a water utility. We can calculate the embedded energy so that when you save a gallon of water in San Diego, we actually have the formula, we actually have documented how to discern the energy embedded in that water from its conveyance, its cleaning, its distribution to customers, and then if it is in fact recycled, it's recycled, the energy embedded there. But what we don't have is a regulatory pact that allows us to account for that embedded energy. So that's the stalemate that we are in right now in California that has kept us from having what I call an integrated resource efficiency program. So after working in the trenches for 4 years to try to help craft a regulatory approach that accounts for embedded energy, I will say in California something really important happened on May 10th. Not enough in the eyes of some, but something for many of us. On May 10th, the California Public Utilities Commission approved an energy efficiency portfolio, in other words, where they expected to ask the investor-owned energy utilities to expend funds over the next 2 years. And for the first time, the decision asked the investor-owned utilities to look at possible combined water and energy projects for energy efficiency, only capturing direct energy. In other words, at the utility scale, saving energy in the utility scale in 2 ways. Possibly through leak loss detection and eradication. In other words, if you have leaky pipes, you're potentially losing if that's treated water, you're losing the energy invested in that treated water, and we're still not to the point where we can account for the energy invested in getting it to that utility. But leak loss detection and eradication, and then secondly, systems optimization, and I didn't say pressure management, leak loss and pressure management, because the two obviously go hand in hand, and then systems optimization to at least make water systems the most energy efficient as possible. Now, in California, frankly, those two aspects already were able to be captured. That's not new. The truth is, the energy efficiency program could already fund, Peter's smiling because he knows this, you could already fund these measures, it's just it didn't happen. And so this was a way of saying, okay, now we really want to see projects to do this. But because the regulatory pact is weak in two ways. One, completely doesn't address the embedded energy side. But secondly, the existing energy efficiency program and agreement, pact in California, requires that the energy efficiency portfolio of each of the energy investor-owned utilities be balanced in a certain way. That pact allows, to the desire of some and chagrin of others, it permits the shareholders of investor-owned utility companies to receive certain returns to their investment in energy efficiency if they perform at certain levels. It's somewhat controversial, not even somewhat, it's highly controversial, and I won't deal with the controversy except to say that this particular pact requires that a very crisp regulatory signal be given to the investor-owned utilities because they're unwilling to take risks that might affect their ability to reach the kinds of performance standards that ensure their returns to their shareholders under these particular incentives that are part of our pact. And I won't go into all the angels on pin heads about this pact, except to say, if you don't give a really crisp regulatory signal under the pact we have, the investor-owned energy utilities will step back and not really step up to the plate with innovative projects. So, let me give you an example. Actually, Southern California Edison has been wonderful in its water and energy program. It has really stepped up to the plate over the last, I'd even say, decade, and trying to use the existing program to work with its, so something that obviously needs to be said, the water utilities are among, if not the highest, commercial sector users of electricity. They are very close to the top. So they have, we in California had and will until the end of December have something called a public goods charge. All of us have a surcharge on our energy bills, and our energy efficiency program is largely funded by about $400 million from our surcharge and another $600 from our procurement fund. So we had up until the end of this December, we will have had about $1 billion a year spent in energy efficiency. Southern California Edison had its account executives on the commercial energy side meeting with some members of the water sector, trying to capture, the allowable programs I just talked about. Why do we care about that? Well, it's so interesting that when we had this decision announced to say, okay, please, bring us projects that capture water and energy, they didn't bring as many projects as they could have because they were not clear what credit they would be given for those projects. And I could say a lot more. I'm just going to say a few things and hopefully we'll have a discussion. But why any of this matters at one level is because we can't make much progress until we change this way that we regulate water and energy together. Peter started by saying, he didn't use the word bifurcated, but that's the problem. We have energy regulation on one side, we have water regulation to some degree on the other side. It's very difficult to almost impossible to integrate the regulation of the two. And for example, on the water side, the Department of Water Resources offers a little bit of carrot, not even so much of a carrot, but not even really a stick, but we at least say now in our urban water management plans, can you estimate the energy use in your water or something like that? And we're not even really clear yet how the water utilities are to do that. But we're getting to the point where we can imagine a world where we integrate energy efficiency in some way, let's say through audits, baseline audits, wastewater treatment plants, in our state funding of, say, water treatment plant expansion or something like that. So we are beginning to see a day when we can at least combine, to make our water systems more efficient with state dollars. But we have so much more we could do in the water and energy frontier if nationally we really deal with a different paradigm for integrated resource efficiency that really does incent the conjoined savings of water and energy as a separate animal. And honestly, it is not because the energy sector is, deaf or dumb or blind to the potential savings of energy in the water sector. It's just that the mechanism for doing it is not yet there. And there is huge intransigence right now in the California Public Utilities Commission in our energy division to accounting for embedded water. So 2 words of embedded water, as I mentioned, is the embedded energy in water is the upstream energy. The CPUC has spent $8 million of ratepayer funding on energy efficiency, embedded energy in water pilots done in the year 2000 to 2010, really trying to measure and estimate and see if one could cost effectively save water and energy together. And they used, I think they had 10 different sector scenarios, vineyards, dairies, a variety of different applications to try to see if it would pencil out to invest energy efficiency dollars in saving water and energy together, or at least decreasing the energy intensity of water-intensive projects. And the findings of that pilot just kind of, the commissioner who was really behind it left, and the findings of those pilots just kind of went away. And those were the findings that were foundational to solving this problem of cost effectiveness and embedded energy in water. So right now, we are waiting for another 2-year cycle in California to have workshops, to perhaps have some more pilots, to see if we can take the findings from the pilots and reach a new regulatory pact that will allow us to save water and energy. I just finished by saying that really the driver here is greenhouse gas emissions reduction, it's climate change. In California, Peter mentioned that water utilities are looking at reducing their greenhouse gas emissions. Lamentably, in my opinion, water is a subsector of the electric sector. It makes sense in a certain accounting way that water as a subsector is not capped, because the first source of most of the energy in the water sector of the emissions is in fact in the energy sector. So we have in California, of the 11 climate change teams, we have the water and energy team of the climate action team. So we have a water and energy team, but we're not capped. We have nothing that makes us, in fact, so the capped sectors, for example, transportation, for example, is probably the largest. Those committees are, that team is really tasked to implement energy savings because they have a metaphorical gun to their heads. We don't on the water side. So we have a really hard time trying to convince state agencies, sorry I'm reminding myself, state agencies or a legislature, I would say, to some degree the governor's office has been a real player with us to help push this, but they also don't have a very strong mandate to demand that we figure out how to save water and energy together. So we are in the climate action team, we are looking at renewables in the water sector. Everything that has to do with saving energy in the water sector is, we are kilonats. That's what I call us, the kilonats. If you're, from the Boston area, that makes you, killer gnats. But, we're kilonats. We don't bring enough renewable energy. We don't bring enough energy demand reduction. The water sector, those of us in the water sector, see the profound importance of saving water and energy together, and I'll finish up right this second. See the profound importance of saving water and energy together. But the energy side of the house, and for some very good reasons, sees those energy savings that we can contribute as being very marginal. The only way to solve that problem is an integrated resource efficiency paradigm. So that's really fundamentally what I think we need to do.
Thank you so much, Cindy. Our next speaker is Professor David Zilberman. He's a professor here at UC Berkeley in agricultural and resource economics. His research interests are in agricultural and nutritional policy, the economics of technological change, and the economics of natural resources and microeconomic theory. Dr. Zilberman received the American Agricultural Economics Association's publication of Enduring Quality Award in 2005, and in 2002 he was presented with the association's Quality of Research Discovery Award. Here on campus, he's recognized as a leader in developing innovative cross-campus collaborations, such as the Center for Sustainable Resource Development, the BEARS Environmental Leadership Program. He's a significant contributor to the Energy Biosciences Institute. He's really the heart and soul of the newly launched program, the Masters in Development Practice from the College of Natural Resources. Please help me welcome Professor David Zilberman.
Okay, I think what I would do is, to some extent, compliment the previous speaker, because I would really look at how energy affects water, and then I try to see how you can put them together. So the talk is called Mixing Water with Oil. About 10 years ago, I organized in India a conference about how high energy costs affect water and how all these things play together when it comes to biofuel and other alternatives. So my perspective, in many ways, is both in terms of agriculture and in terms of economics. So I'll start with something a little bit technical and conceptual, how high energy prices affect water. And this is really, really huge, because when you are in a developing country and you subsidize water and suddenly it costs you twice as much to subsidize water, you have to think about what you're doing, and that may be a main source of reform. So I would really start to look at the reform from a water perspective, and then I'll start to speak a little bit about energy. Now, as an economist, a lot of the notions of water and energy are really linked. People that work on water started to introduce the notion of water use efficiency and water conservation about 30 years ago. And a lot of the techniques that several of us developed 30 years ago in water are now migrating to energy. And I really think that developing an intellectual agenda that mixes the two is very important. But there is one thing that, and I will try to emphasize here, that is very, very important in water, and I think only now people start to emphasize it in energy, is how the legal framework and a lot of the systems that were originated in the past and have antiquity, maybe 100 years old background, really affect what's going on in the present. So to some extent, what you really need to know is to develop a reform, and it's really tough. Now, in my lifetime, the big thing that we did was something called the Central Valley Project Improvement Act. That was the first time that environment was recognized as an element of water, and you start having water trading. I think that today we need some other reforms that would be both in water and energy that would allow much more flexibility and give environmental consideration some equal weight. But let me speak a little bit about the link between energy and water and go from there. Now, generally what we realize that people say water is energy dependent, all the system is water is energy intensive, and a lot of water is used for irrigation, and suddenly from 2005 on, suddenly the price of energy went high, and then there were all a lot of linkages. So the first thing that people say, okay, high energy prices would result in decreased supply of water. People will use less water. My argument that things are a little bit more complex because you need to understand a little bit how water system works. So generally, the impact of high energy prices on water is not clear cut. On one hand, if energy prices is expensive, you pump less water. On the other hand, if energy prices is expensive, you build more hydroelectric power. And a lot of the big water facilities, like in California, are a result of hydroelectric power. So to some extent, you can have something very, very interesting that you can see that with hydroelectric power in some regions, suddenly you'll have cheap water because of hydroelectric power. On the other way, in other regions, because of water scarcity, you will have less agricultural production, so there will be a big shift. In California, for example, there is one good example. We have the area of the Kings River where there was a hydroelectric power that allowed Boswell Brothers and a lot of people to grow cotton. So to some extent, you have to understand what's going on, even though to me the net effect of increased energy prices will be reduction of water. In some areas there are some opportunities, and this is true especially in developing countries. So I work with people in Nepal, in India, in Africa. A lot of times the hydroelectric power will allow you to introduce water product, and you have to do, and this is a challenge is to do it in a way that is not very wasteful, because a lot of time when you have a lot of water that is cheap, people waste it, and that really causes a lot of problems. So that's the first point. So the other thing, so to some extent, you really have a change in the system. Okay. Now, the other point that is very important is that when you have a subsidization of groundwater, when you have a high energy cost, you really get into trouble. Because what really happened in countries like India and in even part of the US, that after many years, the aquifer went down by about something twice as deep. Now you have to pay twice as much for water, so you have to pay 4 times as much as you paid in the past for a unit of water. So that is a real force for water reform. So if I look at water globally, I really see that we are now in an era that energy will change what's going on in water. In some areas there will be more opportunities because hydro, but that wouldn't be that big. But in other areas, you really have to think what to do with groundwater. A lot of water utilities are in town. A lot of the subsidies for water are now unaffordable. So I think that's something that will really lead to a lot of change in water. So to some extent, high energy prices result the financial cost of water subsidy, the social cost of inefficiency, and increase the likelihood of water reform. And to me, the key in water is reforming the system. And how we reforming the system means 2 things. Develops ways that you move water efficiently in an environmentally safe way, and develop incentives to adopt improve irrigation and improve technologies on using water to increase water use efficiency. So, since we are in a moment of crisis, I think that I expect that in the next 10 years, if energy prices continue to be where they are, we will see many more water reform, because water reform occurs only in crisis. I'm a big believer that crisis occur, that reform occurs in crisis, and your role as an academic is to write papers that no one reads for 20 years, but they remember them. And when there is a crisis, they call it. That's what happened to us in 1992. That's what happened when they introduced the water bank. So if you come with these ideas, so to some extent, when you are working in water, it's frustrating, but you have to be ready, because if you don't have ideas, nothing happens. Now, generally, what really is the situation of water is that there is a huge perception of crisis. And in many cases, there is a crisis, but in most cases, the main crisis is a crisis of management, and this crisis now is augmented because it's not only water crisis, it's a water and energy crisis, and in most cases, a lot of it is the issue of management, and with climate change is the problem. So, you need to change your regime. Now, I speak a little bit about the way that I look at the water system. Water system historically were affected by 3 factors: water scarcity, government ability to tax and finance projects, and policy objectives. So if you look at, I go very fast. If you look at historically in the United States, when the government was weak, they wanted the country to grow, but they didn't have money to subsidize it. They introduced water rights, and they told people, you go, you settle, you have the water. And this is, till these days, it haunts us throughout the U.S. And it's not only in the U.S., it's all over the world. People got water rights with no limit, and there is an element of use it or lose it. Now, later on, the government wants people to settle, but was able to raise money through taxation. Then they moved to a system of water project. And again, in the water project, they have the system that use it or lose it, and there was no incentive to conservation. Now, water scarcity leads to water trading, but it's done very, very slowly because of the fact that people have right, how you modify the water right. The big issue in water is not that we don't know what to do, it's how to basically to deal with the rights of different people. I think the people that make most water and most money in water are not water engineers or economists, they are lawyers, because it's a very disputable field. And that's the reason that the good thing in reform, that it allows you to cut a lot of this right. So when you have a financial crisis, you have privatization, and environmental constraints basically start to change the system, but it again encountered all these problems. So I wouldn't go through this thing, but I think that we really need to understand that to some extent, when you have a water system, you really operate in systems of water that are very, very obsolete, and only a crisis will really change it. And the key element in the crisis is to introduce trading, to introduce environmental quality regulations that mean dealing with issues like drainage, dealing with issues of chemical residues, dealing with issues which are really important, how you keep water for wildlife. That is really, really, but every time that you start to move water, you have environmental amenities that you lose. So you have to combine, and the other thing is to change the design of water projects. I think one of the things that we have in life is the biggest actors in water system are all the big engineering firms that they don't care about water. They care about putting as much concrete as possible. So to some extent, to think about the reform that have different incentives, different environmental regulation, and different design of institutions. Man, I've been working with the government for 15 years on something called the new principles and guidelines that will have a little bit more sound principles of design of project that will introduce the environment. And it has been the approval under the president for 2 years for approval, and it has been approved. So these are the three most important issues. Okay, as I said before, the transitions are not alike. Usually crisis trigger transition, and to some extent, we need to develop the intellectual capacity to think about what type of new water system we take into account, combining it with energy. Now, I can speak about it, but one thing that is very important is when we look at water pricing, and the same is in energy pricing, we need to have a system where the price of right. And generally, if you look at the system, you have the pumping cost, the conveyance cost, the environmental cost, and the future cost. So you have to be in a point like A, where you take into account all these costs when you allocate water. And generally, we are in a point like N, where we subsidize water. So when we are moving from A to N, what happens is that we use more water, we use more energy, and the biggest cost of water system in many cases is the energy that's required. So if you move to a system that basically takes all this into account, suddenly water becomes more expensive. And I speak about agricultural water, but it's even true in industry. And if they become more expensive, people start to think about a lot of interesting things. They don't grow, they don't irrigate every crop, they use efficient technologies, they really look at the drought tolerant, not as some exotic option, but something for real. And I think that is one thing that is really important to move it. Now, as I said before, on one hand, moving to the right prices, taking into account all the costs, allowing basically developing a system of transferable rights, which is a huge challenge, can result in a stable system that will require water and will reduce energy costs. Now, so to some extent, we need real pricing and transfer to water trading. Now, the other thing that we really need is to need a system that will encourage water conservation. Now, I see both in water and in energy, a lot of times the key question is, if people can conserve, why don't they do it? And I really think that we have to have some sort of a more realistic understanding of what's going what is causing for adoption of water systems, or energy system, how to induce people to adopt. On one hand is to introduce new technologies and to introduce financial incentives. On the other hand, you really need to recognize that timing matters, that credit matters, and another thing is education is matter. I really think that to some extent, what is really happening in agriculture is that the amount of people that are being aware about all this new option and the benefit of this option is very, very limited. And I think that to some extent, a lot of water conservation issues are not as much in the mainstream. In California, it changed, but in developing countries, it's a big problem. So I really think that you really need not only to think about financial incentives that include some sort of payment based on your actual water use, some sort of discriminatory fee based on what water system that you use, but also systems that will basically help people with understanding what a new technology can do and provide some of the information that relate to gain, because the potential of conservation is global, not only in the US. Another issue that is even more important is groundwater. There is incredible waste in groundwater, and this waste is waste of energy. And to developing a system that instead of subsidizing farmers by subsidizing energy, you charge them the right price and somehow gives them direct payment, this is really crucial. It's a real challenge. Today, when you want to subsidize poor people, what you do, you give them poor input. When you give them poor input, who pays for it? The environment, the future. Developing a system that you basically pay the right price and at the same time move money to help people that are poor, I think is really crucial, especially in the area of environment. I don't believe that we will eliminate water subsidies in developing countries where most of them occur if we wouldn't have a way that poor people would somehow survive. So to some extent, some sort of welfare combined with the water reform is really essential. Otherwise, water reform and to some extent energy reform wouldn't occur. So to some extent, water reform requires reliable information, good economics, effective administration, political skill, and most important, patience. But I really think that we really need to recognize what are the main elements of water reform. And the main element of water reform is having the price right, incorporating, taking into account environmental consideration, not only other consideration, right design for water project, allowing water trading, as well as development of awareness and education. Now, if we look at energy, I think the same thing is true with energy. A key element in energy is to have energy reform, that people will pay the right prices. I think that to some extent we have the same thing. That when it comes to water project, we need to have water projects basically reflect some sort of social rate of return, rather than projects that are determined on a political base. And the third thing, mechanism to assist low-income individuals. The same principle, have the price right taking into account. When I speak of price right, including the environmental price. Develop water projects that are not, that have some social rate of return and assist the poor. The same principle apply here as well as they apply there. Another thing is to develop in both systems issues of adaptation capacity. I really think that the big issue that we will have with both water and energy are what is the issues that relate to climate change. The system will be unstable. So you really need to develop a system that all the time allow you to have mechanism to improve water use efficiency and to adjust very fast. We need to avoid excessive regulation. We need to invest in knowledge. Now, I think that one of the big issues is that when we try to look at climate change, we have to recognize that climate change will shift our system. California will move, Los Angeles weather will move here, our weather will move to Oregon. Farming system will have to move, we'll have a lot of problems because trees cannot walk, pests can. So we really need to develop a system, we need to develop a system that would allow us to adapt. And this system, on one hand, is a system with the price of right, and the other hand is a system that really allow us to take advantage of technologies as we can, as much technology as we can. I really think that a lot of time as economists, we overemphasize regulation and we underemphasize technology. I really think that with climate change, we have a technological race against evolution and against the changes in the climate. And if we don't develop the technology and we don't develop mechanisms to introduce it very quickly, we are in trouble. Now, everyone knows that I'm a big proponent of genetic modification. The reason is that we really will need to have a huge change in our biological system. We need to develop new crop system as our agricultural system moves. And to some extent, when we look at all these changes, it's not only changes in our regulatory system, but ability to introduce new technologies very safely. Now I go to biofuel. So the biofuel, of course, is to some extent is controversial, and in some areas when biofuel, when you grow a biofuel crop and you grow food, you have some of the dilemma. In most cases, though, when it comes to water, especially irrigation, both biofuel is not irrigated, but still the issue when it comes to corn, obviously there is this dilemma, and we worked on it a lot. But on the other hand, when we look at some of the new direction to develop biofuel, there is a lot of potential to grow biofuel feedstocks in areas where there is water abundance and for whatever reason underutilization of land. In many areas, for example in the southeast, basically there is a lot of water. The land is not the best land in the world. You cannot grow the corn, but you will be able to grow a lot of other energy crops. So to some extent, that is one point that is very important. Another challenge of biofuel, and I think is to use marginal water that are somewhat more saline than usual. So again, development of research like the EBI and other things all over that will allow you to increase your portfolio of ability to utilize water resources so you don't compromise your food system, but to, on the other hand, develop renewable energy system, I think is really important. So if I summarize all this, this point is crisis is triggering change. We need to have a water resource management that have principles of introducing the right prices, designing projects that make economic sense, taking into the environment into account, and considering poor people. And you need the energy reform, and most important, and in addition, you need to continue to pursue technologies that would allow you to introduce this, that would allow new incentive to be implemented effectively. Because I think that with climate change and the scarcity of energy that we are facing a real challenge if we really don't want to screw ourselves up. Okay.
Thank you all so much. So let's have the speakers transition up to the table up in the front and initiate a panel discussion. And David, I understand you have a prior commitment that you need to leave at 10 to 12? first to see if we want to put a few questions out there resulting from the presentations that might start the discussion going, and if not, I'd be happy to start myself.
Thank you very much for all the speakers. I would like to share a couple of challenges that we are facing related to water and energy issues, especially in Malaysia. I think applies globally as well. One of the challenges is actually about funding. Traditionally, people would like to see water and energy as separate issues. Well, you know that. One of the challenge that we are facing is to get funding, because in Malaysia in particular, large funding is allocated to fundamental research, and when we try to do projects related that integrates energy and water, evaluators typically don't see as water and energy as an integrated thing, and they don't see the fundamental aspects of the thing. What Peter presented, especially, well, they say you just calculate the impact of using energy on water and vice versa. That is quite straightforward to them. So what are the fundamental things that you are trying to develop here? So maybe you can share some of the things. I see policy as one of the things, but coming from engineering perspective, they don't see policy as having scientific elements in it. That's one of the challenges. The other challenge we are facing is what you just mentioned, most speakers have mentioned as well, is that especially on the regulation. Yes, I agree that traditionally there are regulation worldwide, globally. If you are aware of any regulations, that it has been a model that we can emulate, that would be very useful for us to point towards. You see, you mentioned that these are also the challenges that you are also facing. Is there anywhere in the world, anywhere else in the world, that you can see a model that integrates water and energy in the policy? Our project, for example, our proposal go as far as integrating not just energy and water. We're talking about energy, water, and CO2 emission. So they are very much integrated, and we are proposing an indicator for the three, what we call as green management system or green indicator for process plants. So we're trying to develop something like this, an indicator that has impacts on the three things. So, but that is not being bought by the people. That's my questions.
So the second question is looking for other international models that have.
Other international models that we can emulate.
And then the first question was specifically, what are the engineering challenges to the integration of the water energy mix?
Yes.
Okay.
Then, what are the fundamental issues that can be dealt with from the scientific point of view related to energy water? Otherwise, they will be seen as straightforward calculations. You see, there's not very little research element from the scientific point of view. That is how people see it.
I think that one thing that is really important is that politically, almost in every country, when you have a Congress or a Senate or Assembly, there is a water committee, energy committee, and agricultural committee. They have their own budget. If you start to integrate them, then it's a problem. So basically, a lot of time you have an institutional setup that's based on historical fact that really allocate things differently. So to some extent, start to educate people that two are integrated, really make a difference. What happened in California was that we have a Department of Water Resources, and it was a reform that happened 40 years ago, and therefore air and water at least speak with one another. In the US government, now we have a process that takes about 15 years to try to integrate energy, agriculture. So all these things, so a lot of time, it's not so much engineering. It's a lot of time in the administration system and the way that politicians work. So to some extent, you really have to educate people and to show them, okay, that's what you can gain. And then you develop political structures that really allow you to mix the two. Because I think that is something that we went through, and it took many years to develop awareness that the two things are connected.
How effective has it been?
Oh, I think that we are now doing much better than we did many years ago. But still, in the United States, it's a big problem. You have an agricultural committee; they won't give the power to something else because there is something small called climate change. You know, there is the transportation. So to some extent, but it's really happening. People develop. So you really have to convince people and to educate people and to say, go see how much you lose. Like there's a reason that worked like Peter did. To take study to demonstrate how solving one problem and the other separately is not good. You really need to integrate. It's a global problem, and I think that to some extent you really have to show that it's relevant to the people that you are dealing with. If I tell you that it's work in California, they say, will it work in Singapore? So you really have to demonstrate that they again.
Cindy or Peter, do you want to add?
I was just going to say, you know, in some ways, climate change is the great savior in terms of trying to do water and energy together. You're just referring to this because in California, to give you an example, okay, we have a statewide, you know, way that we calculate greenhouse gas emissions and that we calculate avoided costs and avoided energy costs, and we can translate that to greenhouse gas emissions. Some folks in the water world have said, okay, let's translate the energy savings from water into greenhouse gas emissions. It's not, you know, rocket science. I mean, I'm not an engineer. It's not higher mathematics. It's pretty simple algebra, actually. So we have been able to do that and say, okay, let's compare cost marginal water supplies, just like this, the bar chart that Peter showed looking at the energy intensity of water. Well, let's look at the avoided cost by using local water supplies instead of imported water, for example, in California, because we move water up and down. It's pretty simple to say, okay, it's pretty clear that if you want to say reduce greenhouse gas emissions, your choice would be the following scenario in any particular region. We now know how to do that in California. Now we're trying to get to the point of saying, okay, and this is how we're going to implement this knowledge. So in California, we're pretty close, but we're not quite there yet. But it is greenhouse gas emissions reductions that you know, it is climate change that is pushing us to the solution.
Okay, I think we're ready for another question. So speaking of greenhouse gases, when people look at potential energy solutions, I think frequently they'll look at how we can reduce greenhouse gases using this new technology. So it's very complicated to say, to have a multifaceted view because it's many factors play into this. You could look at from a water perspective saying, this technology would be good, but maybe it doesn't offset greenhouse gases as much, or vice versa. It's good for climate change, maybe it's water intensive. So moving forward, how do you guys think of embracing all these different metrics and restraints for deciding policy?
Comment on trade-offs.
Yeah, I think that's the key point. In the past, when water wasn't scarce or when climate wasn't a problem, we didn't care so much. And so we could build energy systems that were water intensive or greenhouse gas emission intensive. But we can't do that anymore. And if there's anything that I think all of us are saying, it's that now that we realize climate change is a real problem, now that we're up against real limits of water availability in the western United States and in India and in northern China and a lot of places, now that we're finally having to some degree a real discussion about alternative energy systems, this is the opportunity to do the right thing, not the wrong thing. So David didn't get to it much. He didn't talk much about biofuels, but the biofuels thing was a good example. Okay, so biofuels that are water intensive. Oh, okay, so biofuels that reduce greenhouse gas emissions, that permit us to produce more energy domestically, they're a great idea if you don't care about water and you don't care about food prices worldwide, but you can't not care about those things anymore. So we had this ethanol policy that turned out to jack up the price of corn and for food, and it led to food riots in parts of the world. I mean, we now understand these things are related. And so the opportunity is to look at them in an integrated way. The opportunity is to get the water savings and the greenhouse gas savings and the energy savings all together, and you're only going to do that if you look at them in an integrated way. And it's much more difficult, and David talked about the institutional issues associated with it, and Cynthia talked about the fact that climate change really has to be a problem, and David hinted at the fact that we don't really do much unless there's a crisis. But which I agree, but we're in a crisis now, and it's an opportunity. I think we need to think about it as an opportunity.
Did you want to comment on something?
I think that what really happened is that we now start to developing in the background a lot of models that are integrated. Models that combine the greenhouse gas effect, the water effect, and to some extent, we really have to continue and improve these exercises because developing some sort of trade-off, and we really have to learn how to work with smooth diametrics. In economics, it's easy because you translate it to price, but the reality is that you need 3 or 4 dimensions. What is the water effect, what is the energy effect, the greenhouse gas effect, etc. And what really makes it different is that in different locations, the price is different. In Canada, the impact of water is different than in Jordan. But I think we develop this type of capacity. And as we have this capacity, and it's reliable, our biggest problem today is that we have this model and people don't believe them. So we have to improve them. But once you develop this model, then when something happens, you come to policymakers and say, okay, is that what you can do? I really think that, I think that reform will happen. The question is, we have to be ready to come with good ideas.
Can I actually say one more thing about that? It gets to the first question. It's not an engineering problem. I think we have the tools to do the kind of analysis and integration. It is an institutional problem. So, for example, the Pacific Institute, we developed a model called the Water Energy Simulator, working with water utilities to help them understand their energy demand and their greenhouse gas emissions. But the problem, as Cynthia says, there's no institutional requirement yet that they use them, or there's no benefit to them necessarily of implementing the savings until there's an economic approach or until there's a regulatory requirement. So we have to get the institutions right.
So you're also saying that globally there is no such,
And there's no global market for carbon, or there's, but they are, we're starting to develop those. We have them in California now.
Got a question in the back row.
Yeah, hi, Heather Youngs, Energy Biosciences Institute. Just to kind of follow on the question about multiple metrics, I guess first I'll make a comment. The suggestion of putting kind of the water metrics in terms of greenhouse gas emissions, I think is very problematic because it doesn't address the very local watershed nature of water issues that greenhouse gas doesn't necessarily have. So I think getting to Padma's point about using multiple metrics, this is something that really does need to be developed. And I guess I was wondering if the panel has any information on how the EU is trying to work water into their sustainability standards for the RED.
I would just recommend you have a look. There's a very interesting 2008 paper from the California Sustainability Alliance. If you go on their website, it's titled something like Recycled Water, the role of recycled water in reducing, in energy efficiency and reducing greenhouse gas emissions. It's a completely localized Southern California study. And what they do are they take local water, not watershed, but hydrologic region water attributes, water supply. And they apply this avoided cost approach that I'm discussing. But they take, because it's kind of complicated, but because we, for a very good reason, look at the avoided statewide energy costs for greenhouse gas emissions reductions. It's not, water is local, and this is part of the problem that you point out. Our water supply issues are very much local. Our greenhouse gas emissions issues are not, they're global, they're not even regional to Southern California. But, you know, mathematics is kind of the best way to in some way interpret the, I mean, really, it's multiplication. Take the avoided statewide energy costs that we assign, which in some way is sort of a benefits measure of greenhouse gas emissions measures. And if we combine those with local water supply metrics, I'll just call it that, we can approach, I think, a pretty reasonable way of saying what local water supply portfolios are best for the water supply issues in different regions, but are, let's call them, made energy aware by using avoided cost mechanisms that are in our case statewide. And I mean, I can say a lot more about that, but the point is we have to have some way of combining something that is in fact local and something, and another resource which is profoundly local. And I think we can do that. We do make the mistake if we do not take local water supply very seriously.
So does that, I'm sorry, just to follow up, does that include weighting factors for example, scarcity within that local watershed or water quality?
It's not meant to do that, but I'd be happy to talk to you more about that afterwards and have a look at that paper. I think you will find some answers to some of your concerns.
Did you want to speak to that question of scale and integration?
I think that I did some work in Holland. Now, in Holland, basically, so what really happened is that basically you look at the water, the water problem as a local problem, the water quality is a big issue. So they really solve all, and then every solution has a greenhouse gas coefficient. So to some extent, what really happened is today you have two common denominators, dollars and greenhouse gas emission. Everything else is translated to these two things. And when both the Italian and the Dutch develop a national plan, they spoke about other things, but they translate everything to these two currencies. And because these are the only things that are traded. So if you look at the problem, you say, okay, I have two solutions. One solution will cost me such and such, and have this implication locally, and it also will have this greenhouse gas effect. So I really think these are I think greenhouse gases in this regard become really important.
And just one other thing, I would say one of the questions to ask, what's the energy intensity of different water supply choices? And so, that begins to make it clear, we complicate the problem. It's not just, it's not just saving greenhouse gases, nor is it just which is the most abundant water supply, but it's bringing those together. And when you do that, looking at, for example, Peter's bar chart, the energy intensity of desaled water is still so high compared to recycled water, it's very clear what the right choice is.
Second question.
My name's Ardith Barnhart. I'm from the University of Arizona. In our state, we're very far away from any discussion on emissions of carbon. But we are considering developing a lot of solar energy for natural reasons. We did a study that showed that if we met our renewable energy standard using all solar parabolic trough, which is a solar thermal technology that's the highest water intensity on the market right now, we would be using 1/16 of the total water balance in our state. It's highly unlikely that we will actually implement any solar thermal technology in Arizona, with the exception of one plant that's going in for APS. The question becomes, in our state, an investment choice based on allocation of groundwater. So people need to understand the trade-offs they're making when they make an investment choice in a technology, a housing development, expansion of municipal services. The choice has come down to understanding the balance of the groundwater. I think we can easily make an argument about energy intensity and technologies and showing distributed generation can offset and even replace some of our dirty coal plants and move around our water, maybe even cost effectively in the next 5 years. But we really don't understand how to inform people about the trade-off on groundwater choices. Do you have any insight on how we can approach that?
Just the data point, actually, I was going to say this. So Peter said that the State Water Project is the largest user of energy in California. Well, it is, but with one exception. At least our embedded energy and water pilots show that groundwater pumps in California, when they are run at the highest times of peak demand in summer months, actually their combined energy use is greater than the combination of the State Water Project and the Central Valley Project together. Now, the question becomes, most states, certainly ours, we don't have a lot of data on groundwater, and we don't really know we have some data on groundwater pumps, but we need to know how many are diesel, how many could benefit from fuel switching. I mean, there's a lot of data to be gathered, even about existing groundwater pumps in a place like California, to say what would be the best energy efficiency program targeted at reducing the energy intensity, or the energy efficiency of groundwater pumps, and hence the energy intensity of that water. So I'm not sure that's an answer to your question, but I just wanted to give you that anecdotal evidence from us here. Problem, challenge.
So at least Arizona has groundwater law.
Yeah, right.
Something California has not managed to do. And at least I gather from your question that Arizona is considering the water implications of central solar thermal plants in the desert. I hinted at the fact that California is wrestling with this a little bit too and requiring dry cooling rather than other kinds of more water-intensive cooling systems. But there will be a limit in the Southwest, which is water constrained to central solar, which raises the question then, is there an additional value to distributed rooftop photovoltaics associated with the water cost of these other alternatives? There ought to be some kind of subsidy to decentralized PVs. I'm not sure, but those are the kinds of policy questions that come up when you start to think about water and energy together. Arizona, I think it's Arizona. Is that what Palo Verde nuclear plant is?
Yes.
All right, so Palo Verde nuclear plant in Arizona is the only nuclear plant in the United States that uses treated wastewater for cooling. Mostly we treat wastewater, we throw it away, but it's turned out to be an asset for Palo Verde, which doesn't have a whole lot of other water available for cooling systems. It's another sort of funny example.
We have to pump it to the plant, but yeah.
Yeah, but that plant would not have an alternative.
Right, exactly.
Okay, our last question, thank
A
you.
small comment on the agricultural aspect. Those of us in the agricultural world, if we're using GMO plants, it takes a lot less water to produce X amount of nutrient. If you're using non-GMO plants, it takes a lot of water to keep those unwanted plants growing. It takes a lot of energy to harvest those crops that were grown without control of both insects and unwanted plants. And that's not something that's often considered, but when I look at the bottom end of the balance sheet and what it costs me to harvest the organic material, just to harvest, let alone to grow, let alone the amount of water that I need per acre, it's considerable, and it really hits my pocketbook. But I go to a lot of meetings over the last X number of years, and there's really nobody talks about what that cost is. We can tell you, because we have kept a lot of records since 1952 on this particular item, and I'm not a proponent of anything in here except my pocketbook. And most of us, I think, would do the same thing in whatever we're doing, but some of the times we forget also when we talk about water consumption, how much of the water that actually goes out for growing those commodities, whether it's tomatoes in California or spinach or whatever, that goes out there that actually goes back through tile to the creeks, that actually goes to the groundwater, that actually goes to the aquifers. I never see those numbers when I sit there with DOE and EPA in Washington, D.C. Nobody seems to come up with those numbers, or what's that percentage? It's all about what went in, but nah, nobody talks about how much of it really was not used. I just make any comment.
Let me respond to that. I won't say anything about GMOs because I don't know anything about it really. I'd be interested to see some of the numbers about the water implications as a way of thinking about the broader implications. But on the water efficiency side, certainly in California, and we've done a lot of work on this at the Pacific Institute, there's a great deal of interest in understanding the full water balance, not just the water that's applied, but return flows, evaporative losses, unproductive evaporative losses versus productive evaporative losses. Because we're now at a point where we can't, there's no more water. The Central Valley of California is just a fantastic place to grow food, but we're water constrained. So the debate now, and there's a growing demand on the urban side to move water from ag to urban, because the cities will pay a lot more for it. So if we want to keep growing a lot of food in California, the debate is efficiency and productivity. Can we grow more food with the water we're already using? Or the same amount of food with less water? Those are productivity improvements, and they get right to your comment about the water balance and where it's going, how much can be recovered, how much really is lost. all of those issues, so we're aware of them, and I think there's been some effort to try and quantify those, but
And as we go off to the global warming side, please understand those areas of the world where we've had a lot more temperatures that do not go down at night, in other words, warm night temperatures. We have crops which are drought resistant, quote unquote. We do not have crops that can withstand hot night temperatures, and it requires water for evaporative cooling to keep those plants alive. And so your production.
We're doing a project right now to look at increased water demand in agriculture, not just agriculture, but also outdoor landscaping from global warming, from higher temperatures, from
Especially evening higher temperatures. we're thinking
another topic.
All right, well, thank you all very much for your questions and your participations. I think lunch is next. Is anyone knowledgeable about where we're transitioning to?
Right, well, first of all, on behalf of the Council of Energy Research and Educational Leaders, I want to thank our speakers, a little gift here courtesy of the Energy Biosciences Institute. Thank you, Carolyn, for moderating the panel. So the logistics are simple, that as you walk out the door, there's food. And we encourage you to take advantage of the solar energy provided here and get out of this building, get some fresh air for an hour. And please do come back here at 1 o'clock. The session on tech transfer will be in this room, and the session on energy education will be in the next room, room 250 up there.
Let's do one last thing.
Yeah.